Hello, this is our single tone instrument identifier by 12 String Consulting. And it consists of Gavin, me, which is Devin, Devdeep, Jacob, and Neel. Okay, just by listening to this audio, you probably wouldn't know that the instrument that was being played was a piccolo. This is where our program slash product comes in. Our product takes in instrumental audio and uses that audio to determine the type of instrument that was played so you don't have to. So here's an overview of our product presentation. So first we will describe the possible use cases of our project slash product. Then we will go over a general description of it. Next, we will give a demonstration of our product being used, and then we'll give a few test cases that we used on our product. Finally, we'll do an analysis on our the overall results of our program and determine whether or not it is available for consumer slash corporate use. So our program is useful for both individuals and organizations or corporations. So for individuals, it can just be used recreationally. If you want to just know what instrument was being played in your favorite music, this is your go-to program. Our program can also become a component of other products in larger corporate companies. For example, Google already has an audio detection device that tells people what song is currently playing in their surrounding environment. If we just add our instrument identifier program to it, it would be a lot better. Finally, our product can also help with search sorting algorithms relating to instruments. So this can be marketed towards companies like Apple Music, Tidal, and Spotify. And it makes it possible to search music by instrument. This can help those companies because it can bring in a lot of classical music enjoyers onto their platform. Here's a general product description. So our product or prototype of our product takes in a single tone A440 audio input and outputs the instrument. And currently it only works for pianos, clarinets, tenor saxophones, and bass clarinets. And as basically our program works by matching the input signal that comes in with perfect control signals that we have stored in the program. So to do this, our program has a step-by-step process. So after opening the program, the calibration occurs first so that it can prime the input signal that's coming in later on for comparison. Next, it takes in the input signal through a live audio recorder. After this is done, we can now apply the calibration to the input signal and match it with we can match this calibrated input signal with the controls and return the instrument associated with the control signal.
Okay, I'm going to walk you through our front-end GUI. So on the left-hand side, under the logo, there is a button that says how to use this program. Upon clicking it, it pops up this little window that gives some instructions on how to use the program. You hit OK, and you jump back to the main window. On the right-hand side, there's three buttons: record, calibrate, and analyze. Record, you click it, you record your instrument, you click it again, and it's done. For calibrate, when you hit calibrate, it brings up click to begin calibration. You hit begin, you wait 15 seconds, and then calibration complete comes up. You hit OK, and you're back to the main menu. After hitting analyze, now with your recorded signal and calibration, you then get the picture and instrument name and how confident we are that we got the correct instrument. Now, calibration. In order to count for the specific acoustics of whatever room the instrument is being recorded in, a calibration is needed. We're doing this via white noise. White noise is played in the room for some time, and it effectively, quote unquote, fills the room, generating a vector that would represent the acoustic qualities of the room that the instrument was recorded in. Following this, the white noise vector must be then combined with the instrument recording vector using element-wise multiplication, which should adjust the signal for the room acoustics. However, to combine these two vectors, they must be the same size, which is where interpolation comes in.
So if the two vectors you want to combine are different sizes, which they likely will be, we have to make them the same size. And this was done using a method called nearest neighbor interpolation. And the method was used twice, once for calibration and once for analyzation. For the calibration, the white noise tends to be a longer vector than the instrument vector. So usually the interpolation shrinks the size of the white noise to match the size of the instrument vector. And for the analyzation, it interpolates the test instrument vector into the control instrument vector, resizing the test vector to be the same as the control vectors. In both scenarios, once the vectors have been interpolated, we can properly combine them using element-wise multiplication. And then in order to compare the vectors, we use dot product. A comparison between the test instrument vector and the control instrument vectors has to eliminate any possible noise differences. So for example, if someone decides to play an instrument at double the volume that our controls were recorded at, these values need to be ignored. So that way our comparison cannot take into account the volume. So our program runs the dot product comparison with all of our controls and the test vector. And whichever control vector results in the highest dot product value is the instrument that's predicted. This dot product value is also what's displayed as our confidence interval.
Hello, this is 12-string single-tone instrument identifier demonstration. First, Jacob's going to play a white noise, and then we're going to record it using our GUI. All right, and now we're going to play an instrument and try to identify it. All right, now we're going to play the recording back through Jacob's speakers and re-record the instrument.
All right, now we're going to compare this calibrated instrument signal with our controls.
And as you can see, after comparing with the controls, our program has determined that we were in fact playing a tenor saxophone with a confidence interval of about 27%. And so now we're going to try it with a second instrument.
Okay, now we're ready to record. All right, now we're going to play it back through Jacob's speakers and re-record the instrument.
And once again, we're going to compare this calibrated input signal with our controls to figure out the instrument.
As you can see, it is a clarinet, and we are about 65% on our confidence interval for that, so pretty good.
All right, so let's talk about how we tested our program. So for testing, what we did essentially was we just ran through the program. So we did the calibration, and then we made the recordings, and then we did the analysis in order to determine what instrument and what confidence we are in that instrument. And then we recorded all this data for 10 trials. And what we found out was that it seems that clarinet and piano are much more accurate than bass clarinet and tenor saxophone, as they have lower false rates. However, this is incorrect, as clarinet and piano were recorded using the original audio we used to make our control signals, and bass clarinet and tenor sax were recorded on my hardware. So the hardware differences have a high chance of accounting for the reason between the correctness discrepancies. And what we determined was instruments tested on original hardware were more successful. And in general, piano is the most often instrument chosen, even in error.
All right, prototype analysis. So for our current prototype functionality, the GUI is complete and visually appealing. The prototype can correctly identify 4 different instruments, and our confidence value displays the accuracy of the prediction each time. The improvements necessary, or that we would recommend before sale, we want to expand the product capability, and we want to improve accuracy and eliminate sources of error. So for some recommended capability improvements that we want to make, the software cannot interpret multi-tone inputs. So that would be something that we'd want to make happen before we make our final sale. We could integrate our software into a mobile application for more users to be able to have access to this software. Currently, it requires very specific hardware to function, so that's kind of annoying, and it limits the amount of uses that this software can be used for. And the calibration system is really cumbersome. Currently, the white noise has to be played from a separate device in the room. We'd like to eliminate that. And our prototype only accounts for 4 different instruments, so we'd like to incorporate a couple more instruments to make this software something that would be more useful. Improving accuracy, our confidence percentages tend to be low. We would recommend that more controls and testing be done. We could use advanced learning or advanced machine learning or neural networks that could greatly improve our recognition by expanding our control base and our database. And the software has to play through a specific set of speakers. So if we had a wider data set, then it wouldn't be so specific for the speakers. That wouldn't make so much of a difference. And our control notes were not perfect. We weren't able to record our controls in a completely perfect environment. So if we were able to re-record even more controls, it could help improve our accuracy too. Thank you. Feel free to read more about our software in our report. And that's everything. And here's our references.